So now we are back to the third speaker and moving to Prof. Ahmed Ennaoui. He is our speaker now. Prof. Ahmed, he is the VLU founder, president of the Scientific Council of Arizona, former managing researcher group at Helmholtz Zentrum Berlin at Germany. His presentation title will be about R&D opportunities in photovoltaics, discussing results on ink formulation and inkjet printed thin film material from lab to fab. Prof. Ahmed served as a professor of physics at University Mohammed V, Morocco, and moved to Germany to conduct research for his habilitation, and completed his habilitation at the Hahn-Mittner Institute at Berlin, Germany. He served also as head research group at Helmholtz Zentrum Berlin for materials and energy, and as researcher as research director of Solar Energy Group at Environmental and Energy Research Institute. Meanwhile, he serves as joint professor at Hamad bin Khalifa University. He published more than 300 scholarly contributions, including 200 peer-reviewed research papers and numerous invited conferences keynotes. He is listed by Stanford University as one of the top 2% of researchers in world out of 224,856 researchers in applied physics ranked by the prestigious American University. Professor Ahmed also, he is a permanent member of the editorial board of Solar Energy Materials and Solar Cell, and senior member of IEEE. During his career, he supervised more than 40 completed theses, and 15 postdoctoral have worked in his group. Currently, he is serving as president of the Scientific Council of Arizona, deeply engaged for the establishment of mechanisms to support and reinforce R&D and on renewable energy, and the evaluation and monitoring of Arizona projects. Prof. Ahmed, please welcome. Prof. Ahmed, you are muted. Prof. Ahmed, you are muted.
Yes, sure.
Yes.
Sure, I have to go again. Okay. And just give me a second. So I hope now you hear me.
Yes, we can hear you, and the presentation is. Go ahead.
Okay, thank you very much. So today I choose many issue for photovoltaic research, and also you have already two of them in the two talks, but I will give an overview of this. But I am also interested in discussing a little bit politics regarding the transition to decarbonized economy. And then I will say just some issue about going from silicon to second generation of solar cell and the third generation in terms of research and development, R&D. And then I want to give some example about my last research before I get retired on ink formulation and inkjet printing of solar cells. Okay. But let's go back to this topic here. As you know, that we have now planet B, and we have to take care to get rid of carbon dioxide in the atmosphere, and to stop using technology that run on fossil fuel if you want to be safe on our planet. If we continue business as usual, we will have some problem, because the carbon dioxide into the atmosphere will create a lot of problems. And actually, that's what we are doing, because we use a lot of oil and carbon-based resources. The renewable energy in the mix is very small. I wrote here 4%, but maybe it's 10% actually, because this diagram is a little bit old. But we have really to go to hold either this actual amount of billion of ton of carbon dioxide in the atmosphere, and to use some technology which even can let us cutting the current emission, and by absorbing the carbon dioxide through different chemical process. So we have to explore technologies that run on green fuel. يجب أن استكشاف التقنيات التي تعمل بالوقود الأخضر. Okay, so if you look to this diagram here from IRENA, that the ultimate goal is to keep this 1.5 degrees and to start with zero emission. This means we use industry that doesn't put in the atmosphere too much carbon dioxide. And we have to eliminate the CO2 emission from the industrial process. That's the advice from IRENA in a report what I saw just few time ago. So the baseline emission, we know that it continued to rise until now, but of course the politics have planned scenario to flatten this emission, that we stay with what we have actually. So that is the schematic from IRENA here as a source. And for the 1.5 degree climate target, global CO2 emission need to drop to net zero by 2050. We know this, as you see in this schematic. So there are many industry. There is the transport, the building, the power and heat plant, the industry. Everyone has to do some work in order to drop the CO2 emission. And I just put here how things can be. This is a planet scenario by IRENA here. Okay, so of course there are 6 components of the transition strategy. There is the renewable energy, energy efficiency, electrification, and so on. And these, that is what in the report of IRENA I saw. So the total mitigation for 2050 should be done in this way. Okay. So biomass also, and removal of CO2. So this diagram show you how we have to work together in order to, or how the politics should make rules in order to get to be safe in 2050. Okay, here, for example, how to accelerate the energy transition. There is energy efficiency, there's renewable power use, electrification of heat and transport, innovation, something that we don't know now, but the researcher can innovate and find out, other carbon removal and circular economic. Of course, we have to see how much, if we do all this, how much fossil fuel and nuclear will be. And that's the diagram, what the prediction of IRENA here but it's now how it is in 21 to 2025 and to 2050. Okay, so the measure on industrial emission, the export. I just want to give you one example how the measure should be. The export of the national clothing, for example, and textile sector are estimated at about 36 billion dirham. And I'm talking about Morocco. صادرات قطاع الملابس والنسيج الوطنية تقدر بحوالي 36 مليار درهم. For example, if you export T-shirt to Europe, and your carbon dioxide emission, for example, is 1,000 kilo to produce 1,000 T-shirt, for example. The carbon signature is, we can say that 1,000 grams per T-shirt. If Europe require, for example, they make rules and they require 600 grams per T-shirt, you will pay a tax of 400 grams per shirt exported. So therefore, tomorrow, if the Europe make rules for taxes for carbon dioxide or for carbon, then we will have problem with our export. Therefore, it's very important to start now this energy transition. So how do we measure the carbon footprint in our industry is very important. We have to find rules just now, and how we can effectively reduce the carbon footprint in our industry is very important. This is just because we hear a lot in the social media, in the press about the mixed in Morocco. And in 2020, after Said Gamira, he's a consultant in Energy 4.0 management, he thinks that we don't do enough. So the mixed is very small. You can see it here in this diagram. So we still have 67% of carbon-based energy. And we have just a little bit of solar. So therefore, our mix in energy, our mixed or electricity mix in Morocco is poor, still poor. Donc, we have to work very hard in order to achieve what Morocco have said in the COP20 in Marrakesh, for example. This and what the King Mohammed VI, he says that we want to generate 52% of Morocco electricity from green energy by 2030. Okay, so now I just put here a photovoltaic portfolio from lab to fab, and I made here, according to my knowledge, that there is the PV and grid. We have to work on it. So it's a engineering school in Morocco have to do this job and to work. University also, they are making applied research and how to optimize power electronic for the network connection. So the power electronic is very important. Then for the introduction of photovoltaic in the building, what we call building integrated photovoltaic is very important. We have to have from one side rules that people or folks can make building integration, PV integrated to the building, and we have to have engineer, architect that they work together to do this kind of job. Then the PV reliability, storage, and mobility is also another part of the portfolio for e-car, for electronic car, either the hydrogen car or battery, lithium battery based car. So it's very important. And also we have to work on the injection of the photovoltaic in our electricity network, and all the physics and smart grid method to do this. So here are the three, my recommendation for the programs and the syllabus in the university when they are interested on PV and also on energy transition. So, of course, I show you again this schematic, how we see from our side at the virtual learning university, that we come from knowledge development to the research and development, and to the proof of concept, and to go to the technology readiness level, and to have a relationship to the industry. And we have also to focus on prototyping. So this is the diagram, what we think is very important. Okay, so this is, of course, depending on what we want to, which industry we want to develop. Everything here is open to discussion to know from the beginning. When you start by simulation and modeling, you know exactly which industry you are targeting, and you can make your the education in the university according to this. Okay, so of course, PV technology is not just for producing electricity; it's also to produce hydrogen. So green hydrogen means that you use either wind energy. I'm not talking about wind energy in my talk, but photovoltaic will play a huge role to produce hydrogen, and this is very, very important. And also the storage of hydrogen, and one of the topic what yesterday it was discussed by Professor Benius is the two-dimensional material. So the absorption, desorption of hydrogen. You can store hydrogen in materials, and by heating you can get your hydrogen out, and this you can make a device based on 2D materials in a car, and you can switch your hydrogen from this material into the fuel, to the fuel cell here, for example, and you can get oxygen from the atmosphere, you produce electricity, and you can run a car, for example, like the schematic here. And of course, you need where you can take hydrogen. You should have a hydrogen tank somewhere, everywhere in Morocco. So there are many topics here for research and development. For example, if you take the fuel cell, you have the catalyst. Actually, platinum is very, very expensive. You have to find new catalyst and new membrane also. So all are open for research and development. Okay. So of course you can also try to work on production of hydrogen by either directly by injecting injecting electricity into the electrolyzer, or the direct one what Thomas Hannabel have discussed today in detail, using by mimicking the nature and using the electrodes in this electrolyzer as semiconductor electrode. And of course, there are many things to do in terms of catalyst for absorbing from the industry the carbon dioxide, using from one side the green hydrogen and carbon dioxide from the industry to absorb this CO2. And this is belong to this energy transition. Also, you can use this green hydrogen with nitrogen to produce ammoniac, which is through this Haber-Bosch process, and to get for example, the fabrication of fertilizer. All are topic in research and development, and the materials for catalyst are very important. So now I have the approach in photovoltaic, what always show to people, we have to see what the nature, the photosynthesis is doing. Photosynthesis, for example, is taking carbon dioxide from the atmosphere, mixed to water, which is coming from the earth, and producing the glucose, for example, biomass. And all these phenomena are based on light absorption, charge separation, charge transport, and electricity is produced either as electricity for lighting, or it can be used to make hydrogen and oxygen, or to fix CO2 into other fuels. That's also one strategy where chemists and physicists can work together to make to do R&D. And of course, you have to work with semiconductors, and you have to play with the band gap, with the absorption coefficient, with diffusion length and carrier type. All this was discussed by Thomas Hanabil talk, bulk and surface recombination, and this is the problem of interface, which are very, very important. So the electronic and electrical property, like doping, interface property, catalytic property. So all these are subject for R&D. And it's very important to try to see the problem as simple as possible, where you have two material, one donor and one acceptor, in sandwich between one anode and one cathode. That's the principle. So donor acceptor principle. Now, where we are with the silicon. The first technology in silicon, what we call aluminum back surface filled, where in the back contact you have aluminum, it was gone until 20% efficiency. So aluminum back surface filled. And then it's saturated there. Then people in the research and development, they have gone further and they make what we call PERC. So it's the same, but you have to make some passivation rare contact. And dielectric passivation, local contact opening here but with laser, and the efficiency have increased into about 23%. Then afterward, there are research on using much more complicated, but using the photolithography, for example. Inject printing also now, it's also used, and to get more better efficiency until 26%. And now, of course, there are research, and Professor Nasruddin have talked about it, to use high efficiency crystalline silicon and high efficiency perovskite, for example, to take the whole spectrum and to get very high efficiency. And this is very, very interesting topic. You have seen Professor Nasruddin have made solar cell with very high efficiency, already above 20%, 22%. And imagine you add silicon there, then you will go at around 30% efficiency solar cell. And this is also there are a group, they are working on to make together perovskite and silicon together, either as monolithically integrated or only physically integrate one over the other, and to see how it works. So the light which is not absorbed in the top cell will be absorbed in the bottom cell, and then you can get this. That's the scenario for silicon and switching to tandem with perovskite, which is one of the topic actually very hot. Let's see here that there is a logic going from silicon into two binary compound to ternary compound. That's what always I show here, and you can see that for silicon it's very easy to dope the silicon and to make solar cell. But when you go to binary compound, it depends which binary compound. If you go to 2,6 compound, for example, then you have the problem of doping and defect. We have to deal with this, and one has to study this. But if you go to the direction of 3,5 compound, then this is the way where it's like a textbook. You can use the background from silicon for doping, and you can make, for example, tandem cell, like what Thomas Hanabil have discussed, with 3,5 compound and to make a very high efficiency. Actually, it's 45% as he showed before. And all this, there is a way to understand the physics behind. And also for chemists, you can also study the Gibbs diagram and to see where you can make your, where it's situated the best stoichiometry for your compound. So you can go from silicon to 2,5 to 2,6 compound or 3,5 compound, and then you have chalcopyrite, this copper andium gallium selenide, or kysterite. This is also one way to do R&D, and there are a lot of research opportunity here to study the stoichiometry, the band gap. When you make alloying with gallium and sulfur, for example, in case of chalcopyrite, and the doping and the binative defect, you can also have a lot of background there. Of course, there are many ways to build up a graduate core curriculum syllabus based on basic research opportunity. One can make his syllabus just from research, and that's why it's very important that a professor at the university has to be a good researcher and doing research, in order that they always make their concept for their course, for their syllabus, according to their research and according to what's happened. So, and there are a lot of issue here, what I wrote. I will not go through, but you can read it. And the band gap engineering, for example, is very important. Ab initio and density function theory is very important. And then you can always see with some method, like X-ray photoelectron spectroscopy, Auger electron spectroscopy, you can see what the theory say and what the experiment is doing. And you can know the defect structure, the surface, the measurement and optimization, etc. Okay. Now we go to 10 films. 10 films is just, if you compare silicon, which you need at least 200 to 300 micrometer to absorb the enough light. For 10 film, you need only 1 to 6 micrometers. So you will gain in terms of amount of material. As you see here, imagine that you have a hamburger with the same amount of energy than another hamburger, but what is more slower. So 10 film technology is very important because you can gain in terms of cost. So the high absorption coefficient, the direct band gap, the minority carrier diffusion length, the band gap engineering, heterojunction structure. So all this you will find it in 10 film technology. And you can see here, for example, the light can be absorbed until the minority carrier diffusion length. And the minority carrier diffusion length has to be as is given by this relationship, which is the diffusion and the time constant of recombination. So, and here is the absorption coefficient. That's the material when the light is absorbed. So you can have, if you have a high absorption coefficient, you need less material to absorb the whole light. Okay. Now, the technology, once you know everything and you develop the basic, the technology became very easy. And this is, for example, a technology that I know very good because I worked on. So you can use, for example, andium, gallium, selenium, and copper to make copper, andium, gallium selenide or sulfide selenide solar cell and modules. And once you have a good solar cell, you can scale up the process what we call monolithic integration technology. And monolithic integration technology is working as follows. You need 3 patterning. So I will explain here how it is. You have the molybdenum. You deposit the molybdenum on glass. Then you have to use a pulsed laser where you cut this molybdenum. This already gives you how much voltage you will have at the end of the day, because you will cut as much as you want here in this molybdenum, and at the end you will gain your voltage. Then you deposit the absorber, that is the andium, copper, gallium sulfide selenide. Then you make what we call rapid thermal processing, which consists of just taking your material in an oven for a few minutes. And then the whole thing, indium gallium sulfide cell, will mix according to the Gibbs diagram. So you have to have already the knowledge from basic science, and then you can make this absorber. Then you will continue the patterning after absorber and buffer deposition. You will make one patterning again, and then this patterning will passivate the surface. And if you have, for example, grain boundary, it will be passivated. That's why we are using weight chemical processing for this, which is very easy to go inside the grain boundary. Then you deposit zinc oxide, for example, on the top, on front contact, and then you will have the whole system where it works like the back contact of one cell is connected to the front contact of another cell, like here. When you see here, that is that's the front contact here, and every gap here is one solar cell, which is maybe a few millimeter or centimeter here, but it's alone 160 centimeter in the other side. And then you can have your monolithic integration technology. So the monolithic integration technology, it's already known. You have just first to make your material with high efficiency, working on the basic physics and basic research. Okay, so here I show you again this. That's the 10-film solar cell, and here the first generation. So that's the first generation here, and that's the second generation. And that's how the copper indium sulfide selenide, copper indium gallium sulfide selenide based solar cell look like. You have the molybdenum here, what you see. You have the absorber, which is copper indium gallium sulfide selenide, is about. I'm sorry here, I made millimeter, but this is micrometer here. I will make it, okay, I will write it, micrometer, okay, good. So you have 1 to 1.5 micrometer here of your CIGS, and then you deposit an extremely thin films of cadmium sulfide or zinc sulfide. My case, when I did my research, I made an alternative to cadmium sulfide. I use zinc sulfide, what we call cadmium-free solar cell, and we have a very high efficiency with. So that's the second generation solar cell. So we did a lot of work on this. Work from lab to fab, and we were able to go from 1 square centimeter solar cell in the lab to high module with 60 to 160 millimeters, so a big module, and we with more than 13% efficiency and cadmium free. You can find this in this publication what we did in Progress in Photovoltaic, for example, here, or in renewable energy. Okay, so again, what Professor Harabil have developed is the what we call the tandem solar cell with the 3,5 compound, and I think he says quite a lot about 3,5 compound, all the challenge, and this is also a kind of solar cell where you can use it with high concentration. You can, for example, use 200, 300, maybe 1,000 sun by concentrating the LIN here, as you see, on your small solar cell, and you can get a very high efficiency, about 45%, 46, I guess, %. And this by combining different band gap, different material with different band gap, and what is not absorbed in one material will be absorbed in the second one. So you have the bottom cell and top cell, and Hanabi, he showed his case where he used different material. He even used now silicon combined with 3,5 compound, and this is also a research opportunity topic. Okay, here Maybe I will recommend you one book written by one colleague in Helmholtz Center Berlin, which is a very interesting book, where he explained, for example, this the quantum efficiency of multi-junction tandem solar cell, where you can see how the whole solar spectrum can be absorbed if you make, for example, germanium, gallium, indium arsenic, and gallium, indium phosphide, for example. And that's the quantum efficiency here. And that's the solar spectrum RM 1.5. Okay, again, I go back to this donor acceptor heterojunction. So we can imagine one material as donor molecule. Just we go back to organic, to another one as acceptor molecule, and in between two sandwich. I think the Professor Nasruddin had talked about this when he talked about the perovskite. And C60 is one of the material which is used. And here I am talking about organic photovoltaic. And so that's how the structure of C60. So this, I just want to say that organic chemists can be involved in this kind of research. And that's how the organic solar cell is working with a donor and acceptor, either as flat or a bulk heterojunction. So you have B layer heterojunction and bulk heterojunction. So there is interpenetration between the two material, donor acceptor, or you have one material over the other. And then there are problems. So the light absorption and exciton generation, because here it's about exciton, not about electron hole, which are completely separated. And then this is very good done. It's already known. The exciton diffusion is one of the problem in this kind of material solar cell. That's why interdiffusion between two materials is better. And then the exciton dissociation is perfect. And the charge carrier diffusion is very good here in B layer, but in the bulk is a little bit difficult because there are some problem, and all are subject for research and development. Okay. Then charge extraction is ZOZO, has also to be studied. So, well, I will go a little bit further, but you know, here organic photovoltaic is very, very cheap. As the same with perovskite also, it will be very cheap. So you need only dye, and then you can make your solar cell. Now I will go to one topic where I worked in. I think 5 years before I get retired from Helmholtz Center Berlin, and we developed one project called Atlet, and then we had a lot of money to do research, and we work on inkjet printing. This is a very interesting topic. I don't know if I still have time. Yes, okay. So the drop-on demand inkjet printing. So you have just to apply a pulse or pressure, or a piezoelectric system, and then you can get, this is the ink heat, it's called ink heat. There are two kinds of ink heat. One, which is working at room temperature, you have the ink, and you can just deposit your ink on substrate. It's like what you do when you are printing paper, it's the same. And there are now companies which are making this print head. That's the most important part of this inkjet printing, and you can see it here, for example. And then you can deposit with the nozzle. You can deposit your bubble on a substrate, and you can. What is interesting on this method is it's a non-contact technique. You reduce the amount of liquid. That's why it's called drop on demand. Just what you need, you put it on the substrate. So this means you reduce the environment impact and the environmental footprint. And you can deposit a wide range of materials that can be deposited: polymer, ceramic, semiconductor, perovskite. That's why I asked Professor Nasruddin before. And then you can also develop algorithm. So all what you wrote in your screen here, the algorithm, or every image you can have on your screen or on your iPhone, you can deposit it on a substrate. So with high resolution digital image, direct image data can be deposited. So there is a tandem between the informatics, the software, and this. So you can imagine a lot of features in this. Almost any object can be printed as long as precise digital data for it exists. Printing ink which solidify after impact on the substrate. You can formulate your ink, the chemistry, and find out as soon as your drop is on the substrate, it can be solidified and crystallized. So that's the principle. And of course, you can connect this with the industry 4.0. For example, you can have a contact with your customer, and the customer can send you exactly what he wants to do, and then you will do it. And you can also have a company in a very small village, for a very small place. So you can localize your manufacturer in some place. So that's the industry 4.0, where you bring to the customer what he needs, what he wish. Okay. So we go back to this stuff. This we can use it to make ink. If you look here, this diagram, we can make ink with one metal, with a second metal from different column of Mendeleev. To make it together, you have to find the right solvent, etc., to make a ink, and the ink can be inkjet printed. Well, I did this work for many years with PhD student, and we deposit, for example, zinc, copper with some, and also some compound which contains the selenium, etc. And we make what we call hot injection, and we deposit, for example, casterite. That's we call hot injection. Then we have here some material, and the other material you can inject it under hot atmosphere. And then you can make directly nanoparticles. This nanoparticle, you can remove the solvent here and replace the solvent by what we call ligand exchange, and then you can make ink, copper poor, zinc rich. You can also, from the beginning, you know that thin, it can be evaporated. So during the annealing, so you have to make an excess of thin that you have exactly the stoichiometry you need. So ion exchange, for example, with this element here, in order that the amount of carbon in your ink will be less. In order when you make your device, you don't have too much carbon there. And you can use the Gibbs diagram for this. We did a lot of very interesting work published. Okay, so here, for example, you can see here how it is after annealing. You have the one drop of your ink contain a lot of information about the adhesion, about the additive, about the wetting process, about the solvent, and the composition, concentration, which are giving the idea about the viscosity. So one drop contains a lot of information, and you deposit it, and after annealing, you get your material. And we did a lot of work. You can I made here some reference here, published in these journal, and we base all our work on Gibbs diagram. And you have made a lot of material. Annealing process, what we call rapid thermal annealing, that you just go from room temperature and you go slowly to the 550 degrees, and then you can have your material. Okay, and then you can see that your grain will increase during the annealing, because copper sulfide, copper selenide, for example, is a melt at 520, I guess, and then it will play a role of flux for the crystallization. We add also some sodium. Sodium also help to make the crystallization. Okay, so here we before we start the inkjet printing, we use spin coating. in order to have an idea about our material. And then we moved to inkjet printing. So spin coating is one method to give you an idea about what the material, what you are doing, because it's very easy to do. And then instead of always using inkjet printing during the research, you should have a spin coating also, in order, after you formulate very well your ink, then you move to inkjet printing, but not before. So we have made a lot of nanomaterials. Well, as you see here, when you take the material after some time, then you can see the size of the material. And we prepare kisterite, for example, copper zinc 10 sulfide nanoparticles, and we made a very good solar cell with. Of course, X-ray diffraction, Raman spectroscopy, and high resolution TEM are the most important method to characterize your particles. So we have a very good success to make a good solar cell with this, based on inkjet printing, preheating for something like 200 degrees to take out the solvent, and then rapid thermal processing to make the grain higher and to make a solar cell. And this we were able to make a very good efficiency, about 11.3%, but it is a result of 2015. And we published this in Energy Environment Science, which is a very good journal with impact factor of 38, as far as I know. So it was a very good work. And of course, we start to work on scaling up using roll-to-roll. We don't finish this because I was retired, so I cannot continue this work, but it's very interesting if people can activate this kind of research in Morocco, for example. And you cannot just think about inkjet printing, you can also think about sputtering, about the PVD, about electrophoresis, where you just apply a very high voltage to your substrate, if it's metallic, for example, and you can deposit your material. So these are all opportunities to go from lab to manufacturing to fab, and to make absorbable like copper, indium, gallium selenide, kisterite, CZTS, OPV, organic photovoltaic, dye-synthetic solar cell, perovskite, etc. Okay. Well, I will not make too much to show too much here, because it's more or less the same. So there is a portfolio to go from a solar cell to module, and how to do this. So I just want to give you the last slide as a conclusion of portfolio, research portfolio. You have the spectrum starting point, the spectrum of the cell. You have we talked about silicon and 10 films, and they show you that you need 100 micrometer of silicon, while you need only 1 to 3 micrometer for the 10 films. You can have, with 10 film, you can have flexible solar cell, flexible substrate to work with it. Then you have tandem cell. There are a lot to do, actually. The donor acceptor system, the production of hydrogen by mimicking the nature. That's what Thomas Hanabil have shown. It's his picture here, what they show. The fuel cell, there are a lot of things to do in terms of catalyst and in terms of membrane. And of course, there are material like the hydrure and 2D materials, what Professor Ben Yusuf have shown you yesterday. So all our research portfolio, and all are based on material cost, production cost, and the power. And this is the most important the equation for this. So electricity, hydrogen, carbon dioxide capture are 3 important topics where the research opportunity exists a lot. Okay, just here my student, my last student for PhD, his name is Lin. He got his PhD in 2015 with a very, very good work. I just kept his photo here, the day of his disputation here. That's myself in the lab when I worked some time in the lab. And thank you very much. Thank you very much for your attention.
Thank you very much, Professor Ahmed, for your presentation. Now we open the session for Q&A. Who wants to write in the chat or wants to speak directly or through raising your hands, please. Let me check now. Yes. Prof. Nazir, you have any additional, any comments? Welcome, please.
No, thank you. So I was following and very nice talk, actually. It's a mixture of several topics Professor Ahmed has covered. I really enjoyed listening to his talk.
Thank you. Thank you.
Thank you very much.
Yeah.
And how about Prof. Ben Youssef, please welcome. Prof. Ben Youssef, the mic muted. Your mic muted, yes. No. Again, Prof. Ben Youssef. Okay, till the time that you check your mic. Any other comments before ending the session and letting Professor Ahmed to give his last conclusion also? Yes, Prof. Ben Youssef, it is opened and it comes again closed. All right. Prof. Ahmed, if you want to conclude your session.
Well, I think there are many issues and research opportunity to do research in our countries, and a lot of things which is not well done in Europe or can be done in our countries because we have time to do it. All what I show is an overview on what is possible to do, and all are related to the energy transition. Sometimes related directly. This means we can have result now, and sometimes related for maybe 10, 20, 30 years. So that's a program where I hope that in the future, in our universities, we don't write a syllabus or program for teaching based on book. We have to write it based on our research and our knowledge. I find that many times we take a book from someone and we just write and say, that's what I would teach. We should not do this. We should make a program based on what you are doing as research. That's my advice. So that's it. Thank you very much.
Professor Ahmed, can I comment?
Yes, sure.
I think it's an interesting approach which you are taking, but this type of courses can be taught at master's level or PhD level.
Yes.
Undergraduate level, certainly they need a foundation, and without basic strong foundation in chemistry or in physics or mathematics, they will not reach a higher level. So, for example, if somebody XYZ wants to teach the subject which he is doing research, that research may not be the subject for the students to learn. So they need a foundation, actually.
Yeah, that's sure.
This approach, please adopt, because up to undergraduate level, they should really follow the basic fundamentals of the particular subject.
Yes, but
provide fundamentals, and then they are capable of understanding technologies. And
absolutely agree with you. My point is, what about one professor? He never do research. When he got his PhD, he just teaching. That's my point, which is touching our country. For me, all professors should be involved in research.
Yes.
Although that's in the first stage, they have to give their lecture according to the textbook, etc. That's true.
Yeah.
But if you take a professor, he got his PhD and then he's teaching for
Yes,
30 years. What do you get from him at the end of the day?
I understand.
A student, he can go to the Google and he can get all the information. Huh?
Yeah, let me highlight one point, because I was in an advisory board of Sharjah College, and it's the same problem. And they are putting 3 publications per professor. And if I look at the budget, they have a 10,000 Swiss francs or dollars, US dollars, 10,000, 15,000. And with this budget, what they are going to do actually research. The UAE like country where people are talking about billions, I was laughing and then told them this is not a way of doing the research, and they want to be on the top of the list in the university ranking. If the budget of each professor is in the range of 10,000, they cannot expect anything.
Yes,
sure. So for doing the research or publications, they need a funding, and the funding has to come from the government actually for fundamental research. So it has to start from the government level to provide the funding. Take in Western countries, each professor, they get certain budget, and using this budget, he can have 3 to 4 PhD students, 1 or 2 postdocs. He can teach, he can continue doing research, implementing his ideas.
Yes.
And if the government, they cannot support this type of funding, the professor, he is doing his job just to take his teaching, is taking his salary.
Absolutely, absolutely. I agree with you. The government has to at least to increase the infrastructure every year and to and then maybe the professor has to find money for to do research, but infrastructure has to be there.
Yeah. Okay.
Thank you very much.
Thank you, Prof. Nazaruddin. Dr. Abdelillah, please welcome.
Thank you very much for this very nice talk and for these hot topics and many in many areas related to I agree with you about the connection of research with education with the program, but that need equipment and also many.
Dr. Abdelillah, your mic just make tune. It seems that it is moving and we cannot hear well. Now go ahead, please.
Okay, thank you.
Okay.
Okay, you can hear me now?
Yes, now it's clear. Go ahead.
I said that I'm very happy with the talk of Professor Ahmed. It's very nice talk, and he cover hot topics and many area on the renewable energy. And I agree with him about the connection of research and education. We have to give lectures on research we do in our laboratory and also modeling and simulation. And to do that, we need some equipment, not always the case in many countries, like in Morocco, for example. It's hard to have equipment to make experiments that we can do in research and to connect that to education. This is the big problem for the connection of research and training and education. Thank you, Dr. Ahmed, Professor Ahmed, for your nice talk.
Thank you very much.
Thank you, Prof. Ben Youssef. Okay. I think we reached the time, but we have 5 minutes. Said related to increase and to develop our education starting from the kindergarten, and this is the things that we needed to improve ourselves, and looking for the 10 years, 15 or years coming. Is there any initiatives, Professor Ahmed, as you see from your experience?
You mean initiative on?
In Morocco or in Arab countries?
In Morocco, actually, there is the whole discussion now. The new Minister of Higher Education is trying to do a kind of bottom-up approach. He go to different region in Morocco. He discuss with the stakeholders responsible of different and discussing how to make a concept for research and development, etc. They start this, but that's not the first time we are doing this. The problem is how to apply this. And therefore, one country in Arab world when I like very much because I spent 2 years is Qatar. They are really giving a lot of money to education. And I think Her Highness Sheikh Hamouza, she's very, very much involved in this, even not only in Qatar, but also helping the other countries. And that's, I find very interesting. And especially young kids to school, etc. This is really a very interesting approach because it's an open approach to all cultures. I find it very interesting. I was very impressed by this. When you go to one kindergarten in Qatar, for example, in Doha, you see how much money, how much resources are given. This is very interesting. And of course, this has to help Qatari people, students, etc., to go further. I mean, in few years, let's say in 10 years, every university in Qatar should be Qatari people. That's what I wish one day to see. Not American, not British, but Qatari. They are teaching, but they start this process. When I was a research director there, and there are Qatari, they asked me they want to go to England to do their study. I immediately approved, and they go to study to do their PhD, etc. Because I find that the best way is this. Yeah. We see in Arabic ما حك ظفرك ما حك ظهرك
لا ظفرك
مثل هكذا.
Thank you, Professor Ahmed Ennaoui, the founder of VLU.